Hello, good morning. This is Mr. Waters, and we're going to continue with our two variable equations today. A little bit more about them. I hope everybody is well and happy and at home. Okay, hope everybody's doing okay. I want to talk about first here. We want to think about Walt Disney. Okay, you may know. And a place in the mountains above Los Angeles, in Valencia, a place called the California Institute of the Arts. Now, if you're in the art world, or if you're interested in art as a career, it's likely that you've heard of CalArts, because it's one of the foremost art colleges in the world for training new artists. Okay? And many famous artists have graduated from there. Okay? And if you're a talented person who's interested in working as an artist, it's a good place to go. However, it's very hard to get into. And also pretty expensive too, as it turns out. So the question is, so where did CalArts come from? Well, that has to do with Walt Disney. Walt Disney, back in the day when he was in his studio or making movies like Snow White or Cinderella, you may be aware that unlike now, all of the individuals, every single frame in those feature-length animated movies had to be hand-drawn by artists. Okay, and in the case of Snow White, it was 1.5 million separate cells or separate frames had to be hand-drawn and hand-colored by basically teams of artists. Okay, well, as you can imagine, you can't just drag people in off the street and say, hey, draw this, because people don't have the talent. And if they have the talent, they don't have the training, knowing how to do it. So Uncle Walt had a labor problem. So whatever else people say these days about Uncle Walt, that was a guy who thought big. So he said, okay, I'll just train some artists. So he and his brother Ray founded CalArts for the purpose of training Disney artists, Disney animators. Okay, and over the years, generations of Disney artists were turned out. Okay, nowadays, of course, they don't do it that way. It used to take, with all that hand drawing, it used to take years to produce one single animated a movie, feature-length movie, 2 or 3 years, and they were, of course, as you can imagine, eagerly awaited. These days, of course, the movies are produced digitally. There's almost no hand drawing. The art is almost all done digitally. Now, it's not that artists aren't doing. It's not that artists aren't doing the compositions and aren't doing the drawing. It's just that the artists these days are working digitally. At least the animation artists are working digitally these days, and it's a whole different field. If you're interested in art as a career, as an avocation, then digital art, then you have to know something about the digital world, probably. Okay, so anyway, how was that done on a computer? Okay, the difference is that on a computer, all those images that we see of people moving and cars driving and, animated landscapes of sky and buildings and clouds and stuff, all of those are represented inside the computer as computer code. And when the artist works to produce those, they work on just like they might use, pen and ink and watercolor or something for a physical medium, they work on an art application which produces the same thing, except instead of producing it on a piece of canvas or paper or something, it produces it digitally. And it's all saved and it's all represented inside the computer as computer code, right? Well, that's where the math comes from. And then we can thank the fact that we can do that at all, that we know how to do that, besides the fact that we have computers. The mathematical part behind that started with the handsome fellow that we looked at last time, René Descartes. Because he dreamed up this abstract way to represent shapes, lines, circles, squares, curves of different kinds. And as it turns out, any kind of a shape. All of those can be represented as mathematical equations. Okay? And since we can represent those shapes as mathematical equations, those equations can be operated on inside of a computer actually much faster than we can do, and so animation can be produced inside the mind of a computer, inside the brain of a computer, using the mathematics. The artist doesn't have to do the math, all right? They just have to be able to run the app. But here's what's going on inside the computer. So the simplest version of this, of our coordinate geometry that we worked on last time, it's called coordinate geometry, formally, was plotting points on a plane. Well, what do we do with those points? Well, if you're a shape, if you're a person on a computer screen walking, an animation of a person walking, those are just points, you understand. And those points can be represented as mathematical equations. And that's how the animation is done and stored inside the computer, is by way of these mathematical, whole series of complex mathematical formulas and equations. Okay? So anyway, the simplest kind of equation that we can work on is something called a linear equation. Okay? And it's an equation that looks like this. X plus y is equal to 3. Okay, now that's an equation, just like 3x equals 212 is an equation. It has solutions, just like 3x equals 12 has solutions. We can divide this equation by 3, and we see that it's got one solution, which is 4. So correspondingly over here, this has solutions here. On this equation, 4 is the solution to this equation, because if we plunk it back into the equation, we get a statement that's true. 3 times 4 is equal to 12. Well, we can do the same thing over here, but this is with 2 variables, right? So what we do, the solutions to this equation over here are represented not by a single number here, but by pairs of numbers. One for x and a partner, shall we say, with y. So all we have to do here is we can list to write down the solutions to this equation, we can list pairs of numbers that in effect, that actually add up to 3. So I'm going to make a little chart here to do that. So here's going to be x and here's going to be y, right? And then this is, so when we add them up, they've all got to add up to 3, right? So obviously 1 and 2 would give us 3. We're going to write that as an ordered pair, like we were doing last time. X is 1, y is 2. This is an ordered pair that's a solution to this equation here, okay? Or x could be 1 and y could be 2. Still adds up to 3. We're going to count those as a different ordered pair. We're calling it an ordered pair because remember, when you graph those are not the same spot on the xy plane, are they? Okay, literally any other combination of numbers will work, right? 0 and 3, 3 and 0. Bad planning here, ran out of room. I'll put some more over here, x, y, and 3. So here is 0, 3, and 3, 0. Both those combinations of numbers add up to 3. So we say that all of these are solutions to that equation because they make the equation true when you put these numbers in for x and these numbers in for y. Remember, these are solutions in the same sense that those are. They make the equation true. More possible if you don't insist that your x and y numbers be nice whole numbers. For example, -1 and 4 would work because -1 plus 4, why that's equal to +3. Or -2 plus 5 is equal to 3. So -2 and 5 would be solutions to that equation. Okay, does that make sense? Okay, and they don't have to be integers. They can be fractions. 1/2 and 2 1/2, for instance, because 1/2 plus 2.5 still adds up to 3. So literally any combination of x, y numbers that add up to 3 could be the solution to this equation. As you can tell, that's a lot. Really as many as we want. We could just keep listing them here, right? Decimals, fractions, irrational numbers. So what we get out of this, besides seeing what the solutions are, is we see that unlike this equation over here that only has one solution, this equation over here, this two-variable solution, has an infinite number of solutions, which is kind of inconvenient if you think about it. Because over here, I can say, oh, solve the equation. And you can go, okay, good. Divide by 3. There's my answer. X equals 4. And we're done, right? But what if I said, solve that equation? Well, as you can see, it's impossible to list all the solutions to the equations, right? So what do? We graph them. So first off, before we get to graphing this here, I want you to be able to, if I give you a pair of numbers, I want you to be able to tell whether it's a solution or not. So again, corresponding to this single variable situation over here, if I had an equation like 3x plus 1 is equal to 10, and I said, oh, is x equals 3 a solution? Is x equal 3 a solution to the equation? Well, how would you know? Well, you'd put 3 in. I'm going to use a different color here. Oh, I didn't use this. I haven't used it. Sorry for the arm. Should bring my pens over here so I don't have to reach across. Okay. I'd put 3 in here. 3 times 3 plus 1, right? 3 times 3 is 9, plus 1 is 10. Oh, that's a true statement, so yes, 3 is a solution. Well, how about is x equals to negative 2 a solution? Well, 3 times negative 2 plus 1. Does that equal to 10? Well, 3 times negative 2 is negative 6. Negative 6 plus 1 is negative 5. Negative 5 is not negative 5 is not 10. So negative 2 is not a solution. And I meant to put, oh no, I did that right. Okay, negative 2 is not a solution because when we plunk it into the equation, it doesn't make the equation true. So like this guy here, is 3, 4 a solution to x plus y is equal to 3? Well, no, because 3 plus 4 is not equal to 3. So that's not a solution. Okay, does that make sense? So the first thing we're going to do here is we're going to check to make sure we understand how we know whether something's a solution or not by asking some questions like this and then literally just checking the answers, right, in the equation. And then we're going to see, well, how do we go about handling, how do we go about representing this infinite number of solutions? We can write down a few, but that's kind of not too satisfying because there's literally billions more that we haven't written down. So how do we handle all of those, right? So anyway, but let's keep going with this here. So let me put up another let me put up another equation. Let's say it's going to be x plus 3y is equal to 18, right? And I'm going to ask you, I'm going to give you some ordered pairs. Is, or rather are, these solutions to the equation? Well, and let's try 0, 6. Let's try 6, 0. Let's try 12, 2. Let's try 2, 12. And let's try negative 6, 4. Okay? So, which, if any of these, are solutions to that equation? Well, what we're going to do, and all we're going to do, is we're just going to plunk those numbers, the first number in for x, because remember, the first number is always the x number, the second number is always the y number, right? The horizontal and the vertical, right? We're going to put these in for x and the y in for y and see if we get a true statement. So is this true? 0 plus 3 times 6, is that equal to 18? Well, yes, it is, because 3 times 6 is 18. Oopsie. 18 is equal to 18, so we just write yes, it is a solution. Let's try this one. 6 plus 3 times 0. Is that equal to 18? Well, no, it's not. In fact, it's equal to 6, which is not, right? 6 not equal to 18, so that's a no. So here's a good reason why we call these ordered pairs. The order that you write them in makes a difference. Because 0, 6, that's a solution. 6, 0, it's not. Okay? All right, how about 12, 2? So let's try that one. Different color here. Okay, so I'm going to put, remember, that's the x and that's the y. So 12 plus 3 times 2. Well, that's 12 plus 6. Yeah, that's 18. So that's a yes. Let's try it the other way around. 2 plus 3 times 12. That's 2 plus 36. Well, that's 38, which is not 18. So no, that's not a solution. Let's try that one, which I just dreamed up randomly here. Remember, that's the x and that's the y. So negative 6, we put that in the x position, you understand? And then 3 times 4 in the y position. Okay, the question is, does that come out to be 18? Well, that's negative 6 plus 12, which is positive 6. So that is a no. So those two are solutions, and the other three are not. Okay, so that's how that works. So now what I want you to do is I'm going to give you another equation here. And so this was example 1, and here is example 2, right? I'm going to say 2x plus 3 is equal to 11. I'm going to give you some ordered pairs here, and you're going to tell me yes or no, are they solutions to the equation or not. Okay, so let's go with 0, 3, 1, 2, and, oh, sorry, not 0, wow, not 0, 3. Don't do 0, 3. That's not the one I want you to do. White that out. I want you to do 0, 11. So are the ordered pairs 0, 11, 1, 2, and how about 4? Wow, I just messed up. Okay, I got to go all the way back to the beginning. Pardon me. This needs two variables. What I meant was 2x plus 3y. Sorry for the confusion. 2x plus 3y is equal to 18, right? And so let's try that out. So let's try, wow, that's, yikes. I don't want to go back to the beginning of the video and talk about CalArts again, so you're going to have to bear with me, sorry. I'm going to take out the 3. You're laughing at me now, I know you are. Well, I'm kind of laughing at me too. I want it to be just y. 2x plus y is equal to 18. So scratch that. That's actually the one I meant inside my head. Okay, 2x plus y is equal to 18. So is 0, 18. I'll change these ordered pairs here. Is 0, 18 going to be a solution? Okay. How about 1, comma 9? Is that going to be a solution, right? And how about 4, comma 6? Is that going to be a solution? So 2x plus y is equal to 18. 0, 18, 1, 9, 4, 6. Try those out like we did here. Okay? All right? So put your video on pause, and when you're ready to check your answers, come on back. Okay, your video should be on pause right now. If it's not, put it on pause. Okay, and you're back. Okay, so let's try this out. Okay, so this is 2 times 0. Putting that, remember, this is the x and that's the y. Put 0 where the x is. Put 18 where the y is. Is that a true statement? Yeah. 2 times 0 is 0 plus 18. So this is a yes. Okay? How about this one? 2 times 1 plus 9. Is that equal to 18? No, it's not. That's 2 plus 9, which is 11, not equal to 18. So that's not the same. So that's a no. Okay, so let's try 4, 6. 2 times 4 plus 6. Is that equal to 18? Okay, well, 2 times 4 is 8 plus 6. Oops. Still not equal to 18, right? So that one is a no. Okay, so I'm going to end this video here because it's getting a little bit long. I'm going to stop here. The next one will be about how we represent the solutions to these. And there's going to be some classwork and homework posted for you to try this out. Okay? Very good. Bye.